class. Today we're going to talk a little bit more about logarithmic functions. So we were talking yesterday about exponential growth and decay. So let's look back at some of these equations. Notice that we have a base of 8 and a base of 2. We want to get them constant with the same on both sides. So I'm going to have this as 2 to the 1/2 power on the left, and I'm going to change the 8 to 2 to the third. And then remember, when you raise a power to a power, you multiply. Then I'd take this and I would take 1/2 and I'd set it equal to 9x minus 6. And I would solve that and I would get x equals 13/18. In a similar fashion over here, notice that we have 9 and 27 as our bases. We realized that 3 would be a good base to have that would connect both 9 and 27. So I would write this as 3 to the negative second, and 27 as 3 to the third. Okay, and then what you're going to do is you are going to take the cube root of that, which would be 3, square it, and you would get 9. And then again, you'd set this equal to each other, so negative 2x equals 2, and you'd get x equals 1. Then I want you to remind, a couple days ago we did a problem where it was 2 to the x equals 10, and we used our graphing calculator to kind of experiment. This is where logs are going to come into play. So we're going to take something which is in exponential form, and we're going to put it in logarithmic form. Okay, and I'll show you how to do that. So this is exponential form. What you then would do is you would take this number, that would become this right here. So basically, when you have a log of 2 base 2 to the 8th, you're asking how many times, what power of 2 does it take to get to 8? So we know that would be equal to 3. So you're going to be asked on a test to go from exponential form to logarithmic form and back and forth. So you want to be comfortable with that. There's some properties of logs that we want to make sure that we understand. So first of all, when we have log base a, so that's general, 1 equals 0. What I would recommend to do is to slide this a over, so a to the 0 power equals 1. That would be the example in exponential form. An example would be this, and you can see that 4 to the 0 power equals 1. So anytime you have a base and a 1 here, it's going to equal 0. What if these two numbers are the same? You can see this would be 7 to the first, which equals 7. So anytime these two numbers are going to be the same, it's going to equal 1. When you have this log base 3 of 3 squared, again, the log, that cancels out, and you're just going to equal 2. In a similar fashion, when you write it like this, 3 to the power of log base 3 of x, those would simplify and it would just equal x. So these are all sort of shortcuts. Okay, so let's look at an example right here. Again, you see that log is on both sides, so then 3 would have to equal x. In this case, you see the bases are the same, log base 3, so then 2x plus 1 has to equal x. And then we solve, x equals negative 1. And this one is similar to the one we did yesterday. X squared minus 6 equals 10. So then x squared would equal 16, and x would equal 4 or negative 4. Now this is where you do need to plug in values to see if they work. And in this case, they do both work. But if you ever have a negative as your final answer here, it's not going to work. And I'll show you that in our graph picture next. Let's see, where was the graph? Okay, so here's our graph. Okay, so when you have base 2, now our graphing calculator, that uses log base 10 as your sort of starting point. But let's use, since we did our parent function as y equals 2 to the x, we're going to try this. So let's first plug in 2 in for here. So 2 to the x equals, so 2 to what power is 2? So that would be 1. If I put a 4 here, that would be 2. If I put an 8 here, that would be 3. If I put a 1 here, you would remember that that would be 0. And then if I put a 1/2, that would be the negative first. So when you graph this, it's going to look like this. Okay, oops. So the red equation, and you can see how these are inverses of each other. Whereas with this, if I put 1 in for x, I'd get 2. But if I put 2 in for x over here, I'd get 1. Okay, so they are inverses of each other. So this is the original exponential growth, and this is the log. So now just take note, the domain of a log is going to be from 0 to infinity. So these are switched, and the range is negative infinity to positive infinity. So you will have to be careful. Sometimes you will have to throw out an answer when you have a log that's a negative. Okay. We talked briefly about E when we're dealing with continuous compounding interest. The way to counteract E is logarithmic, the natural log, ln. And if you take the ln on both sides, you can see that the ln E, that cancels out, so you just get x equals ln of 7. Okay. And you can solve these just like normal. When you're dealing with E, you would definitely want to think of using a calculator. For example, an answer down here, 2.079, definitely that would be on a calculator test. Okay, so just leave that up there. That's our picture of the log graph and the exponential growth. Have a great day.